All right, let's talk about the periodic table. You've definitely seen it before, probably hanging up in a science classroom somewhere. But what if I told you it's not just some boring chart of elements? What if it's more like a treasure map? One that's packed with hidden patterns and secret codes that explain, well, pretty much how the entire universe works. So yeah, let's dive in.
First things first, have you ever stopped to wonder why it has such a bizarre shape? I mean, with all those weird blocks and those big gaps, it looks kind of random, doesn't it? But I promise you, that shape is one of the most brilliant and meaningful designs in all of science. It's a complete guide to how every single atom behaves.
Because that shape isn't random at all. It's a map that sorts the elements based on their behavior, and that behavior is all governed by just a few simple, elegant rules. Today, we're going to crack that code. We're going to learn how to read this map like a pro.
So our first stop on this code-breaking adventure is understanding the one fundamental force that pretty much dictates everything else we're about to talk about. This is the master key. This is what unlocks all the table secrets.
And here it is. It's called the effective nuclear charge, or just ZF for short. All it is, really, is the amount of grip the nucleus has on its outermost electrons. It's the pull that holds the whole atom together, and how strong that pull is, well, that determines an element's entire personality. The easiest way to wrap your head around this is to just think of the nucleus at the center of an atom as a magnet. Its whole job is to pull in the electrons that are zipping around it. The strength of that magnet is everything.
Okay, so there's this constant tug-of-war happening inside every atom. As we move across the periodic table, we keep adding protons to the nucleus. That makes the magnet stronger. But at the same time, the inner electrons kind of get in the way. They shield the outer electrons from feeling that full magnetic force. But here's the crucial part. As you go across a period, that magnet's strength gets way stronger, way faster than the shielding effect does. And the result? A much stronger net pull on those outer electrons.
Okay, so now that we have our secret code, ZF, let's actually use it to unlock the first pattern on our map. The size of the atoms themselves. How big are they? And more importantly, why?
First, a real quick note on how we even measure an atom. Since atoms are basically fuzzy clouds of probability, you can't just use a ruler. So what scientists do is they measure the distance between the centers of two identical atoms that are bonded together, and they just divide that number by 2. That gives us the covalent radius, and that's our stand-in for atomic size.
So what's the pattern? It's beautiful, it's simple. First, as you go down a group, atoms get bigger. This just makes sense. You're adding whole new layers, whole new shells of electrons. It's literally like putting on another coat in the winter. But here's the weird part. As you go across a period from left to right, atoms actually get smaller. I know it feels wrong, right? More stuff should mean bigger. But this is where our secret code ZF comes in. That magnet is getting stronger and it pulls all the electron shells in tighter and tighter, shrinking the whole atom.
Now, that explains neutral atoms. But chemistry is all about atoms gaining or losing electrons to become ions. So what does that do to their size? It's really simple. When an atom loses an electron, it becomes a positive cation. Now, the nucleus's magnet has fewer electrons to pull on, so it yanks the remaining ones in even tighter. Cations are always smaller than their parent atom. On the flip side, when an atom gains an electron to become a negative anion, you've just added more repulsion. The electrons all push each other away, and the whole electron cloud just expands. Anions are always larger.
Okay, let's move on to our next trend, which follows perfectly from what we just learned about size and that nuclear pull. This one is all about how tightly an atom holds on to its electrons. We measure this with something called the first ionization energy. Forget the fancy name. I just want you to think of it as the price to steal an electron. It's the amount of energy you have to pay to just pluck one electron off a neutral atom. A high price means the atom holds on tight. A low price means that electron is easy pickings.
So, what determines the price? You'd probably guessed it. ZF and atomic size. When you go down a group, that outermost electron is way far away from the nucleus, and it's well shielded. It's an easy target. The price to remove it is low. But as you go across a period, the atom is getting smaller, and ZF is getting much stronger. That electron is held incredibly tight, so the price to remove it becomes very, very high.
Now, if you look really closely at a chart of these ionization energies, you'll notice a few little hiccups in the trend, a few glitches. But these aren't mistakes. These little exceptions are actually fascinating puzzles that prove the underlying rules are totally correct.
Let's look at the two main glitches. First, the price to steal an electron from boron is a little lower than for beryllium. Why? Think of it this way. Beryllium's outer electrons are in a really stable, complete set. Boron's outermost electron is the first one in a new, slightly higher energy level, which just makes it a bit easier to remove. The other glitch is with oxygen. It costs a bit less energy to swipe an electron from oxygen than from nitrogen. And that's because in an oxygen atom, one pair of electrons is forced to share the same small space, and they repel each other. Plucking one of them away actually relieves that tension, making it a little easier to do.
You see, those little exceptions actually reinforce our rules about energy and stability. And that same logic applies when we look at the flip side of the coin. What happens when an atom gains an electron? This brings us to our third and final major trend.
We call this electron affinity. It's simply the energy change that happens when a neutral atom accepts a new electron. Now, unlike ionization energy, which always costs you something, this process can actually release energy, which is a good thing for the atom.
So let's make sure we've got this straight. Ionization energy is the cost to remove an electron. It always takes energy, so it's a positive value. Electron affinity is the energy change from gaining an electron. For a lot of elements, this is a favorable process that releases energy, so you'll see it as a negative value.
And the trend here follows our master rule, ZF. As we move from left to right across the table, that effective nuclear charge gets stronger and stronger. The nucleus has a greater pull, so it's more and more attractive to an incoming electron. This means the atom wants that electron more, and the process releases more energy, making that electron affinity value more negative.
So, we've looked at atomic size, the cost to lose an electron, and the energy change from gaining one. And these might seem like pretty small, abstract details, but I promise you, when you put them all together, they explain something huge about our world.
And that concept is metallic character. All those properties we just talked about, size, ionization energy, electron affinity, they are the macroscopic reasons why something behaves like a metal or a nonmetal. It all comes down to how their electrons behave.
Let's just look at this table and see how it all connects. On the left side of the periodic table, we have the metals. They are large atoms, which means their outer electrons are far from the nucleus. This gives them a low ionization energy. It's super easy to remove those electrons and a low electron affinity. They don't really want to gain anymore. Now look at the right side, the nonmetals. They are the exact opposite. They are small atoms with a high ionization energy and a high electron affinity. They hold onto their electrons tightly and are eager to gain more. This, right here, is the very essence of what makes a metal a metal.
So the whole point is that the entire periodic table, and by extension the behavior of all matter, it can all be understood through this simple atomic tug-of-war. The shape of the table isn't weird, it's a perfect map of these properties. So the next time you look at anything, a piece of metal, the air you're breathing, just remember that its properties are dictated by these elegant hidden rules. So how do these tiny atomic rules scale up to build the entire complex world we see all around us? Now that's something to think about.